Good morning to one and all. This session will be handled by Dr. Shankar Krishnapillai sir in the title of Multi-Objective Optimization for Engineering Application. He has done his PhD in University of Oxford. He worked as an engineer in NASA for 3 years. He is a visiting faculty of National University of Singapore. Now he is working as a professor in IIT Madras. He published more than 150 international journals and having a rich experience in this field. Now session is over to you, sir.
Hello, good morning to all of you. I'm happy to give this talk on the topic of multi-objective optimization for engineering applications. And this topic is important because of two reasons. Okay, first,
Sir, we can put in slideshow modes.
Okay, I think I'll switch off my camera first. Okay, so here.
Sir, we can put in slideshow mode also, sir.
Okay,
Yes,
okay. Okay. Okay, this topic of multi-objective optimization is highly important due to two reasons. First reason is that multi-objective optimization occurs in almost all engineering applications, especially in mechanical engineering. So you can see some devices here, this aircraft engine, then the aircraft wing, the seat ejection, then you can see the gearbox, then brake and clutch and all these things. Actually, all these things are multi-objective in nature. Okay, and another important thing is that not many people are aware of this multi-objective optimization. Many people in India are aware of finite element method and things like that. But the knowledge about multi-objective optimization is less. So because of this, I would like to give a talk on this topic. And of the several examples shown here, we'll discuss some of them later in the lecture. So first we look at the theory and the basics. Okay, the first is, what is the meaning of optimization? Okay, so in the Latin language, optimus means best. So optimization means obtaining the best solution under the given limitations or the constraints. So as far as optimization is concerned, the best solution means either minimizing or maximizing an objective function. The objective function is the function which we want to improve, like the profit of a company, or we want to reduce the volume of a box, then objective function is the volume, and so on and so forth. Then the limitations are expressed by the constraint equations. Okay, for example, the stress in a bar should be less than 200 MPa. Okay, so that is a constraint equation. Or the thickness of a cylinder should be less than, say, 5 mm. Okay, so that is another type of constraint. Okay, then you have the optimization variables. So these are the variables that define the objective function. So suppose you want to minimize the volume of an object. So volume is equal to length into breadth into height. So L, B, H are the optimization variables. Then optimization is highly computationally challenging, because in optimization you have to find the minimum most value or maximum most value of a objective function. And sometimes, depending on the surface of the objective function, that can be computationally challenging. So here you have the examples of two benchmark functions, that is Renewable function and Ackley function, which are used to test the optimization algorithms. That is to test the minimizing ability of optimization algorithm. So if you look at the Renewable function, you can see a lot of peaks are there on the top, and there are a lot of peaks in the bottom also. So the optimization algorithm has to find the minima of all these peaks. And you can see that the minima occurs at x1 equal to 0 and x2 is equal to 0. So a good optimization algorithm will correctly find the minimum value of the shuffle function without getting trapped in any of these creeps. So similarly, you have Achilles function, and the optimization algorithm has to correctly find this minimum point of the objective function, and it must not get trapped in any of these small local minima. So you can see that the optimization is a computationally challenging task, and newer and more powerful optimization algorithms are coming every year. So next we look at multi-objective optimization. And so as I told earlier, in most engineering problems, we need to minimize or maximize two conflicting objective functions. Okay. Conflicting means when you try to reduce one, then the other will increase, and vice versa. Okay. So one example is you want to minimize both the material and the deflections in a structure, like a bridge. So these are conflicting, because when you try to reduce the material, then the structure will lose the stiffness and the deflections will increase. So it is actually a type of conflicting objective functions. So typically the solutions are a trade-off between the conflicting objective functions. So the trade-off is in the form of a Pareto optimal curve. Okay, perfect. Between the two conflicting objective functions. So here you can see F1 and F2 are the two conflicting objective functions. Okay, and if you try to minimize F2, okay, minimize F2, then F1 will increase. Okay, and if you try to minimize this F1, okay, then F2 will increase. So all these are trade-off points. Okay, then if you do the optimization of three objective functions, you will get a Pareto optimal surface. So what you see here is the Pareto optimal surface of the maximization of ball bearing optimization. So in this particular problem, you have to maximize three conflicting objective functions of the ball bearing. Okay, like you have to maximize the life of the ball bearing, then you have to maximize the load bearing capacity of the ball bearing, and you have to maximize one more parameter, which I'm forgetting. I think like the temperature resistance, okay, or the wear rate. Okay, so all these are conflicting objective function, and as a result of this, you get a Pareto optimal surface, and each point of the surface, okay, will satisfy all these three objective functions. Well, but each point of the surface is a trade-off between all these three objective functions. Okay, then concept of Pareto curve. Concept of the Pareto curve and the meaning of dominated and non-dominated points. Actually, the top part of the slide is being covered by the menu. Okay, how to remove it, I don't know. Okay, so what is the meaning of Pareto curve and the meaning of dominated and non-dominated points? So we are going to look at this example. We want to minimize the material, and also you want to minimize the deflection of a bridge. That's a structure. So you have two extreme options. Either you can have more material and less deflection. So here you can see that the bridge is quite thick. Okay, so it has more material. So naturally it is more stiff, so it will have less deflection. And on the other extreme, you can have a bridge which is made of less material, that is thin members. So naturally the deflection will be more. So both of these will satisfy the conditions. Okay, but it is a trade-off between material and the deflection. So all possible solutions of this problem. So all possible values of material and deflection of this problem can be drawn in this F1, F2 chart. So you can see some yellow points here, as well as we can see some green points here. So you get a cloud of points. So each point has a F1, F2 value. So these yellow points are called dominated points. Okay, that is because suppose we take this particular point, all these other points below it are having less values of F1 and F2. Okay, so they are better than this point. So this point is dominated by all the points below it. So, or in other words, all the points below it are better than the dominated points. So you can go down like that. Finally, you reach this green points, okay, which are at the bottommost part of the cloud of points. So if you take this, if you take any green point and draw a sector like that, you can't see any other points below it. Okay. So all these green points are called non-dominated points. Okay, that is because they are the most minimum combinations of F1 and F2. So you can't find any points under them. Okay, so the locus of all these green points is called the Pareto optimal curve. Okay, so the Pareto optimal front represents the locus of all the best trade-offs between the objective functions. And the iterative calculation of the Pareto optimal front is one of the most challenging areas of research in optimization. Okay, so the goal of any optimization, the goal of any multi-objective optimization problem is to obtain this Pareto curve, which is the locus of all these green points, which occur at the bottom of the cloud of points. And each of these green points is satisfying the trade-off between the two objective functions. And any of these green points will satisfy your requirement. Okay, then, okay, so we can look at some examples of this multi-objective optimization. Okay, so some frequently used examples. Okay, so this light combat aircraft wing optimization we'll study later at the end of the lecture. Okay, so now let us look at this commonly done optimization of the gearbox. That is multi-objective optimization of gearbox is a great area of research. So basically here you want to minimize this envelope of the gearbox. Okay, and at the same time you want to maximize the power output. Okay, so those are conflicting objectives. Okay, so what will happen is that if you want to reduce this overall, size of the gearboxes, then the diameters of the gears has to be reduced, and the center lines will come close to each other. So now when the diameters of the gears are reduced, then the torque is decreased. Okay, so diameter is reduced, so the torque is decreased. So to increase the torque, then you have to increase the tangential force F on the teeth. Okay, so, and when you increase the tangential force F on the teeth, then the teeth will break because the gear has become smaller. So it is a conflicting objective function. So as you reduce the diameter of the gear, then it cannot transmit much power because it can only withstand a smaller value of tangential force at the teeth. So then the optimization algorithm tries to overcome it by increasing the face width of the gear. Okay, so it will increase the face width of the gear so that the teeth is more strong. Okay, then also as the tooth forces increase, then the temperature increases. So when the temperature increases, then the scuffing constraint or the lubrication constraints will be violated. Okay, then you have to use more viscous lubricating. So all these things will be done by the optimization algorithm in an effort to find the smallest gear which can transmit more power. And the same thing will occur in the multi-objective optimization of the disc brake. So here also, you want to reduce the diameter of this disc brake. And you want to reduce the volume or the size of the enclosure of the brake assembly. Okay, so now you try to reduce the diameter of the disc brake. Okay, then the braking torque will decrease. And to increase the braking torque, you have to apply more force at the edge of the plate. Or in other words, you have to increase the hydraulic pressure here in the in the hydraulic cylinder and the piston. Okay, so this large volume of force will act at the rim of the disc plate as you decrease the radius of the disc plate. Because torque is decreasing and you have to increase the value of it. Okay, so to do that, the algorithm will increase the hydraulic pressure in the brake cylinder. And then what will happen is that as the force increases, then the temperature of the brake drum will increase. And then the algorithm will try to reduce it by recommending better materials for the brake pad and so on and so forth. And similar type of problem will occur in the clutch plate optimization. You want to reduce the diameter of the clutch plate, but when you reduce the diameter, then you need more spring forces at the periphery of the clutch plate. That means you need to use more stronger material and so on and so forth. Okay, then this aircraft seat ejection is also one important area where multi-objective optimization occurs. So if you want to rescue a pilot by doing the seat ejection, then you need to have a high ejection velocity. Okay, so suppose aircraft is like this. Okay, so it will have a tail. So pilot is here. Pilot is ejected like this. So the ejection velocity must be fast enough so that it will not hit the tail. Okay, the pilot has to clear the tail. Okay, but when you increase the ejection velocity, the spinal stresses will increase. And the pilot may suffer some severe injury due to the failure of the lumbar vertebra. Okay, so it is a conflicting objective function. That is, first you want to maximize the seat ejection velocity, and then you have to minimize the injury to the spine. Okay, so there are also conflicting objective function is there. Okay, so these are some typical examples of multi-objective optimization. Okay, then a brief analytical look at the Pareto front. Okay, so where does the Pareto front come from? And why does it stop at a boundary? Okay, so, or in other words, where does this blue Pareto front come from? And why does it not go down like this? Okay, it can go down like this. Why does it stop here? Okay, that is what we are going to look. Okay, so first we look at statement of a multi-objective optimization problem. Minimize the two conflicting objective function f1x and f2x. Then x is the vector of design variables like length, breadth, height, etc. And x is a subset of real numbers. Subset of real numbers means this length, breadth, height can theoretically take values from -infinity to +infinity. Obviously, we engineers take only from 0 to +infinity, but ideally, as per the original mathematical formulation, it can vary from -infinity to +infinity, but you can put a constraint saying that those variables vary from 0 to infinity. And then you have some constraint equations, inequality constraints and equality constraints. So for example, stress should be less than or equal to 500 MPa. Okay, so that is one inequality constraint. And equality constraints can also be given. Okay, so this entire thing is the definition of a multi-objective optimization problem. Okay, so now let us look at how do you get the Pareto optimal front. So let us look at all possible values of x and y. Okay, so x is here, y is here. So all possible values of x and y occur in this constraint region. Okay. Okay, one example is x1, y1 here. Okay. All possible values of x and y occur in this blue region. Okay, now suppose I want to minimize f1x. So these are the contours of the objective function f1 of x and y. And this is the nearest point on the feasible region or constraint region from the center of the objective function f1. Okay, so this red point is the minima of the objective function f1. And similarly, you have another objective function f2. And this particular red point is the minima of the objective function f2. Hello. Okay, so 2 points are there, A and B. So A is the minima of objective function f1 alone, B is the minima of objective function f2 alone. So suppose you want to minimize both A and B. Okay, then all these points at varying distance from f1 and f2 are solutions to your problems. Okay, so the length of the curve from A to B is the Pareto optimal front. So to get to that, all these xy points has to be converted to f1 of 2 values. Okay, all these xy points converted to f1 of 2 values, and this lower left points. Okay, lower left points form the minimizing Pareto front, and the upper right points form the maximizing Pareto front. Okay, so you can see that Pareto front is nothing but a constraint boundary which is converted to f1 of 2 coordinate. Okay, so this constraint boundary from A to B in xy coordinate is converted to f1 of 2 coordinates, and you get the Pareto optimal front for minimizing f1 and f2. Okay, and if you want to maximize f1 and f2, okay, so looking at this figure, what is the maxima of f1? Maxima of f1 will occur here, and the maxima of f2 will occur here. Okay, because that is the longest distance from the objective function. So this area is the maximizing Pareto front, and that will come here. Okay, so that is the explanation for the Pareto. It is nothing but the constraint boundary which is expressed in f1 of 2 coordinates. The concept of utopia point. So utopia point U is the point where the minimum values of f1 and f2 occur simultaneously. So you can see the Pareto front here. This red thing is the Pareto front. So Pareto front can either attain f1 minimum at A, or it can attain f2 minimum at B. It cannot simultaneously attain f1 minimum and f2 minimum because they are conflicting objective function. And utopia point is the imaginary point where f1 minimum and f2 minimum occur simultaneously, and the Pareto front cannot touch this utopia point. Okay, so the point E on the Pareto front, which is closest to the utopia point, is a good design choice, as it is closest to the minima of both objective functions. So ideally, all points on the Pareto front are equally good solutions. But if somebody asks you to pick one point on the Pareto front which is satisfying both objective functions, then you can find utopia point and find the point E on the Pareto front which is close to you. Then you can recommend it to the customer. So now we come to challenges in multi-objective optimization. So here you can see the spread of points of objective function 1 and objective function 2, which are conflicting with each other. Okay, so you can see a cloud of points, and at the end you can see the Pareto optimal points, and under this Pareto optimal curve there is no more points. So that is how you define the Pareto optimal curve. Okay, so what are the challenges? First challenge is to get a good spread of the curve, Pareto optimal curve. Okay, so it must be able to cover the extreme values of the objective function. So that is the meaning of obtaining a good spread. So next is that the Pareto front should have uniform crowding. So here you can see some gaps here. Okay, there's a gap here and there is a gap here. So this type of gaps are not good. There should be uniform distribution of points everywhere. Okay, so that is another condition of multi-objective optimization. And the third condition is that you must have a good convergence. So originally you will be starting from here. Okay, you're starting from here, then you come here, then you come here, then you come here, and so on. And your solution must rapidly converge to the final Pareto optimal, like this. Okay, so three good challenges are there in the multi-objective optimization, that is spread, uniform crowding, and speed of convergence. So various method of obtaining the Pareto front. So first we look at some exact method. So this exact method requires human interaction. So what is done is that first you have to draw the feasible region and draw this constraint boundaries. Okay, so all the allowable XY values are inside the feasible regions, but to obtain the Pareto optimal front, we are only concerned with the boundaries. So what you have to do is that all the points on the boundaries in the XY coordinate, so all this in XY coordinate must be converted to F1 of 2 coordinates like this. Okay, F1 of 2. Like this. Okay, so then the lower left part of the curve will become will give the minimizing Pareto front, and the upper right part of the boundaries will give maximizing Pareto front. Okay, so this is something which can be done fairly easily with the MATLAB package. Okay, but if you try to do this by hand, it is not very easy. Okay, so this is practical for simple cases. So two objective, two variables x and y, and two objective function f1 and f2. And if you have three objective function, you get a Pareto optimal surface. So we can't do that manually. So let us look at the summary of this method. This method becomes difficult for non-linear constraints and objective function. So if you have non-linear constraint, you may get boundaries like this, and you have to interpolate all the points like this and convert it to F1 of 2 values, which is more difficult. Then it's easier for linear programming problem. Actually, this is a linear programming problem. So the edges are all straight lines, and the objective function will also be made up of straight lines. So what you need to do, you only need to convert this vertices to F1 of 2 coordinates, and then you can draw the straight lines connecting them. Okay, so these are the limitations of the graphical method. Then weighted sum method is very popular with many engineers and scientists. So here the weighted sum of the objective function can be minimized. Or in other words, minimize f is equal to w1 f1 plus w2 f2. So here f2 and f1 are the two objective functions. w1 and w2 are the weighting functions. So some conditions are there when you use the weighted sum method. So first is the sum of weights should be equal to 1. So w1 can be 0.1, w2 can be 0.9, w1 can be 0.2, this can be 0.8, then W1 can be 0.7 and the W2 can be 0.3 and so on and so forth. Okay, so then another important condition is that the objective function must be normalized to the same range, and normalization is not easy. So what is the meaning of normalization? So suppose we have two objective functions, F1 and F2. So F1 is a cost, okay, in rupees, and its value may vary from say 0 to 100 rupees. And F2 is say weight, okay, and its value may vary from say 0 to 1 kg. So you can see that F1 varies from 1 to 100 and F2 varies from 0 to 1. Okay, so the ranges are totally different. So you have to scale the values of F1 and F2 such that both are in the range of 1 to 100. Okay, or both are in the range of 0 to 1. Only then you can add them up with the weighting functions. Otherwise, F1 will dominate because the value of F1 can go up to 100 and the value of F2 will go only up to 1. So this F2 term will become negligible. Okay, so to avoid these things, both objective function must be normalized to the same range of values, and normalization is not easy. That we'll see in the next slide. So the theorem says that for positive values of weight, and for a convex optimization problem, then the solution to the weighted problem gives points on the Pareto optimal front. So, okay, so this is the Pareto optimal front. So all these points can be obtained by different values of weight, say 0.1, 0.9, and here is 0.9, 0.1. Okay, and this weight may be 0.5, 0.5 in the middle. So by changing the various values of just okay, so by changing the various values of weights, we get various points on the Pareto optimal curve. Okay, so actually I told earlier that normalization of objective function is not easy. So the weighted sum method itself appears to be very simple, that you just write W1 F1 plus W2 F2 and you minimize the combined objective function. But normalizing F1 and F2 is not easy. So let us look at some method of normalizing the objective functions. Okay, the first method is divide each objective function by the mean value of the objective function within the feasible region. So you have to, okay, so F1 is Fix is the objective function I. So Fi max is the maximum value of that objective function within the feasible range. Fi min is the minimum value of the objective function within that feasible range. So you have to find these values by a separate minimization and maximization of each objective function. And another method of normalizing the objective function in the range 0 to 1 is, okay, that is Fix is the objective function minus the minimum value of objective function in the feasible region divided by the difference between maximum and minimum value of objective function within the feasible range. So you can see that the method is not easy. In order to do normalization of the objective function, you have to do an individual minimization and maximization of each objective function and find the range. Another exact method of doing multi-objective optimization and finding the Pareto front is to use the varying constraint method. So suppose we have two objective functions F1 and F2. What is done is that only one objective function F1 is minimized. Then the remaining objective function F2 is held as a constraint at various levels epsilon within the range of F. So we can look at this figure. Okay, so this shows the plot between F1 and F2. So what is done is that first you have to find the range of F2. So you have to find the minima of F2, you have to find the maxima of F2, and you have to find the range. And this range has to be divided into various levels. Okay, suppose the range is some 10 to 20, then it is divided into 12, maybe 15, 18, etc. So epsilon is 18 here, epsilon is 15 here, epsilon is 12 here. So for each of this case, you have to minimize F1 alone, keeping F2 at a particular level. So what you do is that the minimum value of F1 is this green point, which is a point on the Pareto curve. So similarly, if you take this F2, that is F2 is equal to 15. So if you minimize F1, then the smallest value of F1 is this green point, which is the point on the Pareto front. Okay. So in the same way, you can slice it at various heights, and you can obtain all these Pareto points by doing a single objective optimization of F1 at various levels. So actually this method requires a lot of human interaction. First you have to find F1 minimum, F2 minimum, and you have to divide it into various slices. Okay. So with two objective functions is somewhat manageable, but if you have three or more objective functions, it becomes extremely difficult. Okay, then another method is called goal program. It's a practical method which is used by engineers who don't want to find the Pareto curve. So here the objective function are simply given some known numerical goals, and we check if the objective function can reach those values. So suppose we have two objective functions, F1 and F2, and we don't want to find the entire Pareto front. We just want to find, we just want to check if the objective function values we want will lie on the Pareto optimal front. Okay, so F1 and F2 are two objective functions. So suppose F1 is a stress and F2 is the displacement. So we give some goals. So stress should be less than or equal to 100 MPa. Then this displacement must be less than or equal to 2 mm. So these are some goals which we give from prior knowledge, and we see if the objective function can attain these goals. So what is done is that then the program is rewritten like this. So this objective function becomes equality constraint. We add one slack variable S1. Slack variable means its value cannot be less than 0. It's always greater than 0. So we add a slack variable to S1 so that, to F1 so that F1 plus S1 is equal to G1, and then S2 to F2 so that F2 plus S2 is equal to G2. That is the goal. So if S1 is equal to 0 and S2 is equal to 0, then our goals are attained. Okay, then F1 is equal to our goal and F2 will equal to our goal. So we have to minimize S1 and S2 to 0. Okay. So what is done is that, so this is posed as a goal programming problem. We minimize S1 plus S2 subject to this new constraints. So at the end of the run, we have to check if that this S1 and S2 are becoming nearly 0. So if S1 is equal to 0, S2 is equal to 0, then F1 will equal to this goal and F2 will equal to this goal. And if S1 and S2 are not equal to 0, so suppose S1 is 10, S2 is equal to 20, then there is a slackness of 20 or a gap of 20 in attaining the goal. So what you have to do is that you have to change the goals. So instead of giving 500 MPa, you change it to 400 MPa. And instead of giving 2 mm displacement, you give 1 mm displacement and try again to see if those goals are attainable. Then some heuristic algorithms, these are preferred over conventional methods because of generality. And you can give any number of constraints, not 2 or anything. You can give 3, 4, 5, 6. number of objective functions as well as any number of constraints. And this ease of use means you can use it like a black box. Black box means you are not interested in the internals of the problem. Okay. Then it is very robust and it is also applicable to non-convex problems. So non-convex problem means the objective function has many peaks. That is called non-convex problem. Okay, so heuristic method means rule of thumb or the approximate method. Okay, so genetic algorithm based is there and particle swarm ant colony cuckoo search based is there. So we just look at genetic algorithm based because they are more older and more tried. Okay, so various type of genetic algorithm based methods are there like VIGA, then random weight genetic algorithm, DPGA, NSGA, NSGA2, NSGA3, etc. Okay, the various type of genetic algorithms can be used to do multi-objective optimization. And another important thing is that when you do the multi-objective optimization, you have to check the algorithm's performance. So various benchmarks are there. The benchmarks are there for unconstrained problems and constrained problems. So here we can see a sample of benchmarks for unconstrained problems. So some of these are called ZDT1, ZDT2, ZDT3, etc. So let us look at ZDT1. You can use up to 30 variables here. The range of the variable is 0 to 1, and these are the two objective functions. And here you can see DTI22. So you can use 12 variables here, and the range is 0 to 1. And in all these benchmark functions, the Pareto front is known. So the Pareto front which you get from your algorithm can be compared with the known Pareto front of each benchmark. And then you can check the convergence and diversity by comparing the algorithm generated Pareto front to the true Pareto front. The coordinates of the true Pareto front are known for all these benchmark functions. And then you can get estimates for diversity and convergence. And that diversity means spread. Okay. Convergence means how close your Pareto front is to true Pareto. Okay. Okay, then you have multi-objective benchmarks for constrained problems. Okay, some constrained equations are given here. So all this can, so if you develop a new multi-objective optimization algorithm, that algorithm has to pass all these tests. Only then it will be accepted by the scientific community. So how do multi-objective genetic algorithm work? They broadly follow the principles of single objective genetic algorithm. So all these things. So let us see here. So first an initial random population of n members is generated by the genetic algorithm. So you can see that they can rank based on their fitness. So this point is least fit because it is coming on the top, and all these points at the bottom are best fit because they are coming at the bottom. And some points occurring in the middle, like the blue ones are less fit, okay, or they are moderately fit. So you have to rank all these points. So the best points occur here, then less fit points occur here, and the least fit occur here. Okay, so you have to rank them from best to worst. After that, you have to reject the worst 60 or 40% of the population, and you can do the crossover and mutation of the good members, crossover and mutation of these good members, and you will get the next generation. You can see that the next generation has come down. So some sort of convergence to the, so this is the final Pareto. Okay. So you can see that as you do more and more generation, the Pareto front you get will slowly move downwards until it converges to the actual Pareto front. So how do you check the convergence of the Pareto front? You have to evaluate this area. You have to evaluate the shaded area in each iteration. And once the value of the shaded area converges to a constant value, it means that the Pareto front has converged. So we look at vector evaluated genetic algorithm is the oldest type of algorithms. We look at it. So it's the earliest multi-objective genetic algorithm. So what is done is that if you have n objective function, population is divided into n groups. Each group is ranked on the basis of that objective function only. And the best members of each group are picked up and put in a common mating. And the members from the common mating pool are subjected to crossover and mutation, and we get the next generation. So we look at a schematic diagram of this. So we suppose we have three objective functions, which we want to maximize. Okay. So F1, F2, F3 are the three objective functions. Okay. So let us first generate a total population of n is equal to 18. So this n is equal to 18 is split into three groups of subpopulations. So n1 equal to 6, n2 equal to 6, n3 equal to 6. So this set 1 is ranked based on the fitness of objective function f1. Okay, so here the 6 members are ranked like this. Here 6 members are ranked like this. Here also 6 members are ranked like this. Best at the top and worst at the bottom. Okay, so here also best at the top, worst at the bottom. Okay. So what you do is that you take the best of each set and put them in a common mating. So the best of each objective function is picked up and put in a common mating. So all members of the common mating pool are considered equally fit. So 2 members are randomly. So in the common mating pool, you have so many members like this. So 2 members are taken at a time and you do the crossover and mutation and you get 2 offsprings here. Then you take another 2, you get another 2 offsprings here. Another 2, you get another 2 offsprings here. You have to do until you get 18 offspring. Okay, and then this 18 offspring will again come back here and it will again be divided into 6, 6, 6. So this is how the primitive vector genetic algorithm works. It is not used nowadays. So why everybody use NSGA 2 and 3 nowadays? So the 3 reasons are there. So it has a efficient Pareto ranking concept. Then it uses a crowding distance operator, which gives uniform spread of the points. So you won't get a Pareto front where some points are crowded in some places and where there are big gaps. Then it also uses a concept like elitism. Elitism means ensuring the best solutions of the previous generation is inserted into the next generation. So that's the meaning of elitism. So reason why elitism is used in multi-objective optimization is that in a particular generation, suppose you have some good points. Unless you deliberately insert it into the next generation, those points will be lost and it's difficult to get those good points again. So that is why elitism is used in multi-objective optimization. Okay, so in the other type of algorithms, okay, for example, distance-based genetic algorithm, the fitness of each point is calculated by the distance to the nearest non-dominated points. So you have to calculate many distances. So if you have a population of 100, you have to calculate 100 distances, which is time consuming. So this is the old method, but the NSGA2 uses a purely Pareto rank approach. So here rank of a member is equal to 1 plus number of dominating members. So if we take the point B, you can easily give it a rank of 4. So 1 plus 3. So 3 members are dominating B. So the rank of B is 4. So if we take A, no members are dominating it. So its rank is 1. So lower the rank, better the point. So that is how NSGA 2 works. There's no need to find these distances. Okay. Okay, then another important point of NSGA2 is elitism. That is the best Pareto members of the past generation are inserted into the next generation. So suppose this is generation T. So these are the parents, and these parents have given this offspring. Usually in genetic algorithm, once you get the offspring, you completely forget the parents. So the good genes in the parents are lost. But in the NSGA2, both these parents and offspring are put in a temporary list. So these are the parents, these are the offspring. Okay, then what is done is that the non-dominated parents and non-dominated offspring are deliberately put in the next generation. So this is called elitism. So the good parents are not lost. Okay, the good parents are also inserted into the next generation. Good offspring is also inserted into the next generation. In the usual genetic algorithm, the parents are forgotten once the new offsprings come. Okay, then what about this remaining member? That is this gap. So how do you fill this gap to reach the population? So what is done is that some of the good offspring, which are not non-dominated, is picked and put here. So for generation T, you get generation T plus 1 by first making a temporary list and then inserting the best members here. Okay. Okay, so investigation into hybrid algorithms is an area of research. Okay, because NSGA still does not converge fast for complex problems. So now we look at one example of the application of multi-objective optimization. So multi-objective optimization of light combat aircraft wing, that is simultaneous minimization of bending and torsional stresses. So the wing will have both bending and torsional stresses which are conflicting with each other. Or in other words, when you try to reduce the bending stress, torsional stress will increase and vice versa. Okay, this is the work of one MS thesis student who worked under me. So in the light combat aircraft, the optimization variables are these four elevon deflection and also this rudder deflection. Okay, so this is the rudder deflection and these are the elevon deflections like this. And the two objective functions are written for the torsional movement and bending movement. So these are the optimization variables. Okay, these are the optimization variables. So all the optimization variables must be visible in the objective function. And then large number of constraints are there. So you can see here. So a large number of inequality constraints and large number of equality constraints. Okay, then some variable ranges are there. Elevon deflection must be between minus 2.5 degree and 2.5 or 25 degree. Okay, between minus and plus values. Then actuator forces should be less than or equal to 10 tons. So each of this elevon has an actuator. So the actuator forces must be less than 10 tons. So this is done with the help of a CFD package. So the values from the CFD package are used to do the optimization. So why are bending movement and torsional movement conflicting? So the aim is to reduce the bending moment at the tip. You can see that here bending moment at the tip of the unoptimized wing is very large. So the wing will break. So you want to reduce the bending moment at the tip and increase it at the root because the root of the wing is strong. So you have to adjust the aileron deflection so that you get this distribution of the wing forces. This distribution. Okay. So that is the crux of the issue. But then what happens is that when you try to shift the wind loads towards the root of the wing, when you try to shift it towards the root of the wing, then the torsional movement increases. Okay. So it is conflicting objective function. When you try to reduce bending moment at the wing tip, torsional moment at the wing root increases. Okay, so as a result of this multi-objective optimization, the combined bending moment and torsional moment has been reduced when compared to the original values. Because these are the original values. So the values have been reduced. How is it reduced? Now we take one particular load case, okay, choosing the optimal values of bending moment and torsional moment for a typical load case. So this is one of the typical load case of this plot. So all these are various load cases, okay. All these are various load cases. I'm showing you one of the load cases. Okay, so this is one of the load case. Okay, so you can try to obtain the Pareto optimal front of the bending moment and the twisting moment for this case. So this is the 10th iteration, 30th iteration, 40th iteration, and 60th iteration. By 60th iteration, you are getting a full Pareto front like this. It has converged, and we take the mid values of the bending moment and torsional moment. Okay, and this will occur somewhere here. Okay, it may occur somewhere here. So from one run you get one value, and if you take another load case and do the optimization, you will get another values of bending moment and torsional moment. Okay, so here one problem which we faced is the slow convergence of Pareto front because of the algorithm of the NSDA2. The Pareto front gets stuck here. Okay, it gets stuck here. Okay. So this is actually the final Pareto front. So you have to reach here, but the algorithm is not moving. So what is done is that, so the utopia point is taken as the goal. Okay. The utopia point can be easily found by doing individual minimization of bending moment and individual minimization of torsional moment. So this is the goal, and these are the slack variables S1 and S2. And once you know the goal, you can submit it as a goal programming problem. Minimize S1 plus S2, and the goal is the goal of F1 is the bending moment minimum. The goal of F2 is the torsional moment minimum. And these equality constraints are filled with slack variables, and you minimize S1 plus S2 so that S1 will become 0, S2 becomes 0. Okay, so if you do this thing, you can see that some improvement is here. So if you use the hybrid method, that is NSDA2 plus goal programming, so you can see that the brown part of the curve has come down. So it has obtained a more minimum values. Okay, so in the end, you can see that by conducting the multi-objective minimization of all load cases, flight envelope was shrunk by about 7% to 20% at different points. So you can see that the smallest values are this hybrid values. Okay, this is the baseline without any optimization. Outermost and innermost one is obtained with the hybrid method, that is NSDA2 plus goal programming. So you can see that the flight envelope has shrunk because of the multi-objective optimization. So these optimized values will be stored in the plane's computer. So when that particular load case comes, the elevator values as decided by the multi-objective optimization will be fed to the ailerons, and it will minimize the wing root stresses. So can we stop here, or is the time over?
Maybe we can continue for another 10 to 15 minutes.
Okay. Okay, so this is the example of multi-objective optimization of the aircraft train. So next we look at one example, propulsion shaft realignment of a warship. This is the Indian Navy project. So here goal programming alone was used. Okay. Goal programming alone was used, and this was done as an MTech project under my guidance, and a particular student was from the Navy, and he was given this project by the Navy to do. Okay, so propulsion shaft realignment of warships. So what is the importance here? So in a new warship, before it comes for duty, the propulsion shaft will be perfectly aligned. So it will be a straight line like this. Then after a couple of years of operations, and what will happen is that, so these are all bearings, okay, on which the shaft is supported. So after a couple of years of operation, some of these bearings may move up, some of these bearings may move down, okay, and so on and so forth. And the movement of the bearings can be delta 1, delta 2, delta 3, delta 4, delta 5, delta 6, etc. As a result of it, you can see that the shaft becomes slightly warped up. The shaft becomes misaligned. So then what happens is that the bearing reactions, okay, F apostrophe will become undesirable. So suppose original bearing reaction of the shaft is decided to be like say 200 kilogram force here. Okay, as per the manual, each bearing must have 200 kilogram force reaction. But after the misalignment, this may become like 500 kilogram force, and here it may become like 100 kilogram force, and so on and so forth. So typically the shaft has to be realigned again to be in a straight line. Only then this bearing support reaction will reach the normal values of 200 kilogram force. So how is this usually done? Because we don't know the values of delta 1, delta 2, delta 3, delta 4, etc. And we cannot also visualize this deformed shape. Okay, because the propulsion shaft itself may be 50 meters long. It is not easy to visualize the deformed shape. So the usual situation is that the shaft alignment checks are done in the dry dock once in a while. So after about say 5 years of service, the ship will be brought to dry dock. Dry dock means there will be no water under the ship. The ship bottom will be dry. So then the bearings are moved up and down by trial and error, and the bearing loads are checked with the load cells. So the load cells should indicate 200 kilogram per bearing. Until then, by trial and error, you have to move the bearings up and down, and mainly by luck, after several hours of testing, you can get all the bearing support reactions back to 200 kilograms. So that is the current method. So an accurate method is required whereby we can calculate the deltas, that is the bearing misalignment, such that the support reactions are made equal to the rated reactions once again. So what is done, what we propose to do is that there has to be some methods of finding this delta 1, delta 2, delta 3, delta 4, delta 5, etc. And then you move each bearing down in the opposite direction. So suppose delta 1 is equal to plus 5 mm, or one bearing has moved up by 5 mm. Okay, then that has to be moved down by minus 5 mm. Okay, so each of these delta values can be found out, like 5 mm, 2 mm, minus 3 mm, minus 1 mm, and then the opposite can be opposite displacement can be given to the bearings to make it come back to the original horizontal level. So how is this done? So what is done here is that strain gauges are stuck on the propulsion shaft once, stuck to the propulsion shaft in the beginning. That is when the shaft is a straight line and before any misalignment, of course. Okay, so you can see the bearings here. And you can see that the shaft is simply supported at this bearing. It is simply supported. Simply supported in all these bearings. So in each span, 2 strain gauges are stuck. Each span, 2 strain gauges are stuck. And these strain gauges are zeroed to give a zero strain. Okay, that is before any bearing misalignment, of course. So now the total bending moment of the shaft is bending moment of the shaft due to self-weight plus bending moment due to misalignment. Okay. The bending moment due to self-weight can be easily calculated from the theoretical model of the shaft. So when the shaft manual, they will give the diameter of the shaft, material of the shaft, and length of the shaft, etc. And once you know the density of the material and all these things, you can calculate the bending moment due to the uniformly loaded shaft or the bending moment due to self-weight. Okay. So that can be done from the theoretical model of the shaft from the optimization manual. Then the bending moment due to misalignment will be straight lines. Okay, because it is simply supported at these spans. Bending moment due to misalignment will be straight lines like this. Okay, so 2 strains are enough to. Okay, the 2 strains calculated by the strain gauges are enough to obtain the straight line bending moment between 2 support points. Okay, so this can be obtained by the strains which are predicted at strain gauges between the 2 spans. So, as I already told you, the strain gauges are set to 0 strain before the misalignment, of course. So any strain in the strain gauges is due to misalignment only, okay, and not due to self-weight. Okay, so that is the importance of checking the strain gauges. Okay, so here you can see that this is the total bending moment. This is the bending moment due to mass distribution, which is known from the FE model. And this has to be, this is the bending moment due to shaft misalignment, which is obtained from the strain gauges. So this is the 2 strain gauge readings. This will give this strain. This is another 2 strain gauge readings, which will give this strain. Another 2 strain gauge readings, which will give this strain, and so on and so forth. Okay. So this way you can find total bending moment of the shaft. So once the total bending moment of the shaft is worked out as discussed, we can find the support reactions. Okay, that is the measured support reactions without the need for any load cell. Okay, so at each support I, the support 1, support 2, support 3, support 4, we can find F1, F2, F3, F4. Okay, so ideal value of F1 must be 200. Okay, like something like that. Okay, ideal value as per the manual. So the goal is 200 at each shaft, at each support point. So now we post this as a goal programming problem. The objective function at each support is a support reaction. Okay, and the goal at each support I is the support reaction as per the shaft specification in the manual. Okay, suppose 200 kg. The goal is that each support reaction must become equal to 200 kg. Okay, so now the optimization variables are the bearing displacement, delta 1, delta 2, delta 3, delta 4, etc. So the problem is posed in such a way that you have to change this delta 1, delta 2, delta 3 in such a way that the F1 will be equal to 200 kg, F2 will be equal to 200 kg, F3 will be equal to 200 kg, etc. Okay. So F1 plus 1 slack variable equal to 200 kg. Okay. So we try to minimize this slack variables. Okay, so we can find the value delta 1, delta 2, delta 3, which minimize the slack variable to 0. Okay, so to test this algorithm, a standard setup was made of a steel rod with attached weight. This attached weight is to simulate the self-weight of the shaft. So this is the steel rod, which is, you can see here, it is supported at various support points like this. Okay. So each of them will represent a bearing. Each of them will represent a bearing. Okay. So the strain gauges are set to 0 values before any bearing misalignment is given. So first the shaft is made perfectly horizontal. Okay. Perfectly horizontal, and all these strain gauges are set to 0 values. Then after that, non-bearing misalignments are given. So how that is done is, this support point is lifted up by +5 mm, and this support point is brought down by 2 mm, and the support point is brought up by 1 mm, and this support point is brought down by 3 mm, etc. Okay, so the various delta values are given, and then the algorithm must predict the equal and opposite delta values to change the bearing, to move the bearings in the opposite direction. So here you can see that some of the trial runs of this. Okay, so in the first trial, the support 2 was moved up by 2 mm, and the goal programming algorithm is giving a value of -2 almost, or -1.76. Then the second support point was moved up by 4.5 mm, and the goal programming algorithm is giving a distance of -4.5 mm to neutralize that. Then another case is there, case 2. So here the second support point is moved up by +2 mm, and the algorithm is predicting -2 mm, or the bearing should be moved down by -2 mm. The second bearing support is given a +6.3 mm lift, and the algorithm is predicting -6, or the bearing has to be moved down by -6. So by doing this experiment, we are able to verify the application of this goal programming method for propulsion shaft realignment. Okay, we can stop this talk now. Thank you. Thank you very much.